Look up at the night sky. What you see is just a tiny glimpse of the vast, mysterious universe, governed by forces so powerful they shape everything from the largest galaxies to the smallest particles. These forces are the invisible architects of reality, bending space, forging stars, and even deciding the fate of matter itself. Some are familiar, like gravity, the silent hand that keeps planets in orbit. Others, like dark energy, remain shrouded in mystery, pushing the universe apart at an ever-increasing speed. Then there are the violent, explosive powers, supernovae, that scatter the building blocks of life, black holes that warp time itself, and cosmic rays traveling across the universe to strike our planet. These forces don't just exist out there, they shape your world, your body, even the atoms that make you who you are. Today, we're diving into the 30 most powerful forces in the universe, uncovering how they work, why they matter, and what secrets they still hold. By the end of this journey, you'll see the cosmos in a whole new light. So buckle up, we're about to explore the raw, awe-inspiring powers that govern everything. And trust me, some of them will leave you speechless. Now, let's start with the force that keeps your feet on the ground and the planets in their orbits, gravity. It's the invisible glue of the universe, pulling everything together, from the apple that famously fell on Newton's head to the colossal black holes bending space itself. Gravity might feel familiar, but its power is anything but ordinary. Think about it: without gravity, Earth would spin off into space, the sun would lose its grip on its planets, and galaxies would fly apart. Isaac Newton was the first to crack the code, describing gravity as a force that pulls objects toward each other, stronger with more mass and weaker with distance. His laws explained why the moon orbits Earth and why tides rise and fall. But it was Albert Einstein who took our understanding to another level. He revealed that gravity isn't just a force, it's the warping of spacetime itself. Picture a bowling ball on a trampoline. The heavier the ball, the deeper the dent, and the more nearby objects will roll toward it. That's how planets, stars, and even light bend around massive objects like black holes. Gravity's reach is staggering. It shapes the universe on every scale, from the way galaxies cluster together to the way dust particles clump to form stars. It's why the cosmos isn't just a chaotic soup of matter, but a beautifully organized dance of celestial bodies. And yet, for all its dominance, gravity is the weakest of the fundamental forces. A single magnet can overpower Earth's pull on a paperclip. That's the paradox of gravity, gentle enough to let you jump, yet powerful enough to hold the universe together. Next time you look up at the night sky, remember every star, every planet, every speck of light is moving to the silent rhythm of gravity. And as we'll soon see, it's just the beginning of the universe's incredible forces. Now, let's shift our gaze from the cosmic pull of gravity to the dazzling force that lights up our world, electromagnetism. If gravity is the silent architect of the universe, electromagnetism is its vibrant artist, painting the cosmos with light, powering our gadgets, and even creating the breathtaking auroras that dance across polar skies. Electromagnetism is the interplay of electric and magnetic fields, a duo so inseparable they're practically cosmic partners. Imagine electricity as a river of charged particles, and magnetism as the invisible current that guides them. Together, they form a force that's a million trillion times stronger than gravity. Yes, you heard that right. A tiny fridge magnet can defy the entire Earth's gravitational pull, showcasing just how dominant electromagnetism is in our daily lives. This force is the reason your light switch works, your phone charges, and the sun shines. Light itself is an electromagnetic wave zipping through space at, well, the speed of light. From the gentle glow of a firefly to the blazing radiation of a quasar, electromagnetism is the universal language of energy. And let's not forget its role in nature's most stunning light show, the auroras. When charged particles from the solar wind collide with Earth's magnetic field, They ignite the sky in swirling ribbons of green and purple, a reminder of electromagnetism's invisible hand at work. But its influence doesn't stop there. Electromagnetism is the backbone of modern technology. Every computer, every power grid, even the Wi-Fi connecting you to this video relies on this fundamental force. It's what allows doctors to peer inside our bodies with MRI machines and astronomers to detect distant galaxies with radio telescopes. Without it, the modern world would literally fade to black. So the next time you flip a switch or marvel at the northern lights, remember, you're witnessing the magic of electromagnetism, the force that illuminates both our universe and our everyday lives. And as we'll soon discover, the cosmos has even more astonishing forces waiting to be unveiled. Now, let's journey into the heart of the atom, where an even more formidable force takes center stage, the strong nuclear force. While electromagnetism lights up our world, this powerhouse operates on an entirely different scale, binding the very fabric of matter together. Picture the nucleus of an atom packed with protons and neutrons. Protons, all positively charged, should repel each other fiercely due to electromagnetism, yet they don't. Why? Enter the strong nuclear force, the ultimate cosmic glue. It's over 100 times stronger than electromagnetism and a staggering 10 to the power of 38 times mightier than gravity. That's a 1 followed by 38 zeros. This force doesn't just nudge particles together, it locks them in an unbreakable embrace, but only at incredibly tiny distances, about the width of a single proton. Without the strong nuclear force, atoms wouldn't exist as we know them. Every element in the universe, from the hydrogen in stars to the carbon in your body, relies on this force to keep atomic nuclei intact. But its role doesn't end there. The strong nuclear force is also the engine behind nuclear fusion, the process that powers stars like our Sun. When hydrogen nuclei fuse into helium under extreme heat and pressure, it's this force that overcomes their natural repulsion, releasing the energy that bathes our solar system in light and warmth. Think of it like this: if gravity is the architect and electromagnetism the artist, the strong nuclear force is the unsung hero working behind the scenes, holding everything together so the universe can shine. And as we'll soon see, the cosmos has even more hidden forces waiting to reveal their secrets. Now, let's step into the shadowy realm of the weak nuclear force, a subtle yet universe-shaping power. While the strong nuclear force holds atoms together, the weak force specializes in transformation, turning one type of particle into another. It's the cosmic alchemist, quietly reshaping matter in ways that make life possible. Take radioactive decay, for example. When an unstable atom like uranium breaks down into smaller elements, it's the weak force at work. This force allows particles to change identities, turning neutrons into protons or vice versa, releasing energy in the process. Without it, the heavy elements forged in supernova would never decay into the lighter ones that build planets, or even your own body. But the weak force's influence stretches far beyond Earth. Inside stars, it plays a starring role in nuclear fusion. When the Sun fuses hydrogen into helium, the weak force helps convert protons into neutrons, releasing neutrinos, those ghostly particles that zip through space almost unnoticed. This process is why stars shine for billions of years, bathing the cosmos in light. Here's where it gets even more fascinating. The weak force is deeply tied to the Higgs field, the invisible energy web that gives particles their mass. Without the weak force, particles like electrons would be massless and atoms couldn't form. It's a delicate dance between forces that makes our universe stable and diverse. So while the weak nuclear force might not grab headlines like black holes or dark matter, it's a quiet architect of change, turning the gears of stellar engines and shaping the very building blocks of reality. And as we'll soon discover, the cosmos has even more extraordinary forces waiting in the wings. Now, let's turn our attention to one of the most baffling forces in the cosmos: dark energy. Imagine the universe as a balloon constantly inflating, but here's the twist: instead of slowing down, that expansion is speeding up, and dark energy is the mysterious force behind it. Scientists first stumbled onto this enigma in the late 1990s while studying distant supernovae. They expected these exploding stars to reveal a universe slowing down under gravity's pull. Instead, they found the opposite. The light from these supernovae was dimmer than it should be, meaning space itself was stretching faster over time. That shocking discovery earned researchers the Nobel Prize and turned cosmology on its head. So what exactly is dark energy? Think of it as an invisible pressure woven into the fabric of space, pushing galaxies apart. Some theories suggest it could be the energy of empty space itself, a concept Einstein once called the cosmological constant. Others propose it's a dynamic force field that changes over time. But here's the catch: we can't see it, detect it directly, or even explain why it exists. It makes up roughly 68% of the universe's total energy, yet it remains completely elusive. This cosmic puzzle challenges everything we know about physics. Gravity should be pulling the universe together, but dark energy overwhelms it, driving an expansion so powerful that distant galaxies will one day vanish beyond our observational horizon. If this acceleration continues, the far future could be a cold, lonely place where galaxies are so far apart that their light will never reach us again. Dark energy forces us to rethink the very nature of reality. Is it a property of space or something entirely new? For now, it remains one of the greatest unsolved mysteries in science, a silent, invisible hand shaping the fate of everything. And as we'll see next, the cosmos has even more astonishing forces waiting to be explored. Now, let's shift our focus to another cosmic mystery that keeps scientists up at night: dark matter. While dark energy pushes the universe apart, dark matter acts like an invisible scaffold, holding galaxies together with its gravitational grip. Picture a spiderweb you can't see, yet its strands keep everything in place. Here's the strange part: when astronomers measure how fast stars orbit the centers of galaxies, they find something bizarre. The outer stars move just as fast as the inner ones, defying the laws of gravity as we know them. According to Newton and Einstein, those outer stars should be drifting away slowly unless there's something invisible adding extra mass. That missing mass is dark matter, an unseen substance that makes up about 27% of the universe. Galaxy clusters reveal even more clues. When we observe how these massive structures bend light around them, an effect called gravitational lensing, the math never adds up without dark matter's hidden weight. It's like watching a pillow depress under an invisible hand. Yet, despite its obvious gravitational effects, dark matter refuses to interact with light or ordinary matter. It doesn't emit, absorb, or reflect anything, making it utterly transparent to our telescopes. So how do we hunt something we can't see? Scientists are tackling this puzzle from multiple angles. Underground labs like the Large Hadron Collider smash particles together, hoping to create dark matter in controlled collisions. Others deploy ultra-sensitive detectors in abandoned mines, waiting for a rare interaction between dark matter and normal atoms. And then there's the indirect approach, mapping its presence through the gravitational ripples it leaves in the cosmic microwave background. The stakes couldn't be higher. Solving the dark matter riddle could rewrite the rules of particle physics and reveal entirely new layers of reality. For now, it remains a ghostly architect, silently shaping the cosmos while eluding our best tools. And as we'll soon discover, the universe has even more extraordinary forces waiting in the shadows. Now, let's journey back to the very beginning, to a fraction of a second after the Big Bang, when the universe underwent a growth spurt so extreme it defies imagination. This is cosmic inflation, a theory that explains how the entire cosmos expanded faster than the speed of light in less than the blink of an eye. Think of it like blowing up a balloon to the size of a galaxy in a single breath. Here's why inflation matters. Without it, the universe would have two glaring puzzles. First, the horizon problem. Why does the cosmic microwave background, the afterglow of the Big Bang, look almost identical in opposite directions? Regions that far apart shouldn't have had time to reach the same temperature, yet they did. Inflation solves this by stretching a tiny, uniform patch of space to cosmic scales, smoothing out any irregularities. Then there's the flatness problem. The universe's geometry is eerily balanced, not too curved, not too warped, but just right. Inflation flattens space like rolling out dough, explaining why we don't see massive distortions in the fabric of reality. The proof, those faint ripples in the cosmic microwave background, like fingerprints left by quantum fluctuations during inflation. These tiny wrinkles eventually grew into galaxies and galaxy clusters, seeding the structure of everything we see today. Inflation isn't just a wild idea. It's a framework that ties together some of cosmology's biggest mysteries. And as we'll see next, the universe didn't stop surprising us after its explosive start. But the universe wasn't done with its fireworks. After inflation set the stage, stars took over. And when some of them reached the end of their lives, they went out with a bang that could outshine entire galaxies. These are supernovae, the universe's ultimate cosmic explosions. Imagine a star many times more massive than our Sun. For millions of years, it burns bright, fusing lighter elements like hydrogen and helium in its core. But when it runs out of fuel, the balance tips, gravity wins, and the star collapses in on itself in a fraction of a second. The rebound from this collapse is so violent that it triggers a cataclysmic explosion, a supernova. The energy released is staggering. For a brief moment, a single supernova can shine brighter than all the stars in its home galaxy combined. But the real magic happens in the aftermath. The extreme heat and pressure inside the explosion forge heavy elements like gold, platinum, and uranium elements that weren't there before. Then the blast hurls them across space, scattering them like cosmic seeds. Here's the incredible part. Every bit of gold in your jewelry, every speck of iron in your blood, even the calcium in your bones, they were all forged in the heart of a dying star and scattered by a supernova explosion billions of years ago. Without these stellar fireworks, planets like Earth wouldn't have the building blocks for life. Supernovae aren't just destructive, they're creative forces recycling star stuff into new possibilities. And as we'll see next, some stars leave behind something even more extreme when they explode. Now, let's step into the darkest corners of the cosmos, where gravity doesn't just bend the rules, it shatters them. Black holes are the universe's ultimate enforcers, regions where gravity is so intense that not even light can escape. Picture a star so massive that when it dies, its core collapses into an infinitely dense point called a singularity. Surrounding it is the event horizon, the point of no return, a boundary where the pull of gravity becomes unstoppable. Cross that line and space-time itself twists beyond recognition. Time slows to a crawl and the laws of physics as we know them break down. But black holes aren't just cosmic vacuum cleaners. They play a crucial role in shaping galaxies, anchoring them with their immense gravity. Many galaxies, including our own Milky Way, have supermassive black holes at their centers, quietly steering the motion of stars around them. In recent years, science has pulled back the curtain on these cosmic monsters. The first ever image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, revealed the glowing ring of superheated gas swirling around the abyss. And then there's Hawking radiation, the mind-bending idea that black holes aren't entirely black. Quantum effects near the event horizon can cause them to slowly leak energy, meaning even these cosmic titans might one day evaporate. Black holes challenge our understanding of reality, bending space, warping time, and leaving us with more questions than answers. And as we'll soon see, the universe has even stranger phenomena in store. Now, let's turn our attention to something equally bizarre but far more compact: neutron stars. Imagine crushing the entire mass of our Sun into a sphere no wider than a city. That's the mind-bending reality of these cosmic leftovers, born from the explosive deaths of massive stars, packed so tightly that a single teaspoon of their material would weigh billions of tons on Earth. Neutron stars defy everything we know about density. But their strangeness doesn't stop there. Some neutron stars, known as magnetars, boast magnetic fields so intense they could wipe data from every credit card on Earth from thousands of miles away. These fields generate bursts of X-rays and gamma rays, making magnetars some of the most violent objects in the universe. Then there's the cosmic gold factory. When two neutron stars collide, the resulting explosion, a kilonova, sends ripples through spacetime called gravitational waves, first detected in 2017. These collisions also forge heavy elements like gold and platinum, scattering them across the cosmos. So the next time you admire a gold ring, remember, it might owe its existence to a cataclysmic neutron star merger billions of years ago. From their unimaginable density to their role in creating the universe's precious metals, neutron stars prove that even in death, stars continue to shape the cosmos in extraordinary ways. And as we'll soon see, the universe has even more extreme forces waiting to reveal themselves. Shifting our gaze to one of the most violent phenomena in the cosmos, we encounter gamma-ray bursts, brief but unimaginably powerful flashes of energy. These bursts, often lasting just a few seconds, release more energy than our Sun will emit in its entire 10 billion-year lifetime. Born from the catastrophic collapse of massive stars or the collision of neutron stars, they are the universe's ultimate fireworks, visible across billions of light years. What makes gamma-ray bursts truly terrifying is their potential danger. If one occurred within a few thousand light years of Earth, its intense radiation could strip away our ozone layer, exposing life to deadly cosmic rays. Scientists believe such an event may have contributed to mass extinctions in our planet's distant past. Thankfully, the nearest known gamma-ray burst candidates are far enough away to pose no immediate threat. Yet, these bursts also serve as cosmic lighthouses. Their afterglows help astronomers map the early universe, revealing galaxies too faint to see otherwise. Some bursts even carry clues about the mysterious origins of heavy elements, much like neutron star collisions. So while they wield destructive power, gamma-ray bursts also illuminate the universe's darkest corners. As we peel back the layers of these explosive events, we're reminded that the cosmos is as beautiful as it is unforgiving. And with that, we're ready to explore another force that reshapes the universe on an even grander scale. Now, let's turn our attention to one of the most dazzling and enigmatic objects in the cosmos: quasars. These brilliant beacons are the hearts of distant galaxies, powered by supermassive black holes that feed on surrounding gas and dust. But unlike the destructive gamma-ray bursts we just explored, quasars shine with a steady, almost unimaginable light, outshining entire galaxies despite being no larger than our solar system. What makes quasars truly extraordinary is their role as cosmic time machines. Because light takes time to travel across the universe, the light we see from quasars today left them billions of years ago. This means we're peering back into the universe's infancy, witnessing galaxies in their most violent and energetic phase. The supermassive black holes at their cores act like cosmic engines, converting matter into radiation with staggering efficiency. But quasars aren't just relics of the past, they also help us understand how galaxies evolve. The energy they release can shape their host galaxies, heating up gas and even halting star formation. Some scientists believe that every massive galaxy, including our own Milky Way, once hosted a quasar in its youth before its black hole ran out of fuel and quieted down. So while quasars may seem like distant, exotic phenomena, they're actually key pieces in the puzzle of how galaxies, and by extension, the universe itself, grew into what we see today. And with that, we're ready to uncover another force that shapes the cosmos in ways both subtle and spectacular. Now, shifting our gaze closer to home, let's explore a force that reminds us just how connected we are to the sun's fiery temper: solar flares. These sudden, explosive bursts of energy from the sun's surface are among the most dramatic displays in our solar system, releasing the equivalent of millions of hydrogen bombs in mere minutes. But what makes them truly fascinating isn't just their raw power, it's how they ripple across space to touch our daily lives. When a solar flare erupts, it sends a storm of charged particles racing toward Earth at incredible speeds. While our planet's magnetic field shields us from the worst of it, these particles can still wreak havoc on technology. Satellites orbiting Earth are particularly vulnerable, with solar flares disrupting communications, GPS signals, and even causing premature orbital decay. Down on the ground, power grids can suffer massive surges, leading to blackouts that last for hours or even days. History offers a stark warning of what could happen if a truly massive flare struck Earth today: the Carrington event of 1859. Back then, a solar storm so intense lit up telegraph lines, shocking operators and setting papers ablaze. Auroras, normally confined to polar regions, were seen as far south as Cuba. If a similar event occurred now, experts estimate it could cripple modern infrastructure, causing trillions in damages and taking years to recover from. Yet solar flares aren't just agents of chaos, they also play a role in shaping space weather, influencing everything from astronaut safety to the longevity of satellites. Scientists now monitor the sun around the clock, using advanced telescopes and early warning systems to predict these eruptions before they reach us. Because in the grand dance of cosmic forces, understanding the sun's fury isn't just about curiosity, it's about survival. And with that, we're ready to venture even deeper into the forces that sculpt our universe. Now, let's zoom out from our solar system and witness one of the most breathtaking events in the cosmos: galactic collisions. Picture two massive cities of stars, each containing hundreds of billions of suns, slowly drifting toward each other over billions of years. These collisions aren't violent crashes but graceful dances, where gravity pulls galaxies together in a spectacle that reshapes the universe itself. When galaxies collide, their stars rarely smash into one another. Space is just too vast. Instead, their immense gravitational forces twist and warp their shapes, stretching them into long tails of gas and dust. This cosmic tug-of-war triggers bursts of star formation as gas clouds compress, igniting new stellar nurseries. The result, a dazzling display of newborn stars lighting up the chaos. One of the most famous examples is the Antennae galaxies, a pair of spirals caught mid-collision. Their long, luminous streams of stars resemble insect antennae, giving them their name. But this isn't just a distant phenomenon. Our own Milky Way is on a collision course with the Andromeda galaxy. In about 4 billion years, these two giants will begin merging, eventually forming a single, elliptical galaxy some call Milkdromeda. While that might sound apocalyptic, Earth likely won't be harmed. The chances of our solar system being flung into space or swallowed by a black hole are slim. Instead, future civilizations, if they exist, would witness a sky transformed, with Andromeda growing ever larger until it dominates the night. Galactic collisions remind us that the universe is anything but static. It's a dynamic, ever-changing arena where even the mightiest structures are constantly evolving. And with that, we're ready to explore another invisible yet powerful force shaping the cosmos. Now, let's turn our attention to something far smaller yet equally powerful: cosmic rays. These invisible, high-energy particles race through space at nearly the speed of light, originating from some of the most violent events in the universe, like supernova explosions or active galactic nuclei. Though they're tiny, their impact is anything but small. When these particles slam into Earth's atmosphere, they create cascades of secondary particles, some of which reach the ground. Surprisingly, cosmic rays have played a hidden role in shaping life on our planet. They contribute to natural mutation rates by occasionally altering DNA, driving evolution in subtle but significant ways. Without them, life as we know it might look very different, but cosmic rays aren't just a biological curiosity, they're a major challenge for space travel. Outside Earth's protective magnetic field, astronauts are bombarded by these particles, which can damage cells and increase cancer risks. Future missions to Mars or beyond will need advanced shielding to keep crews safe, turning cosmic rays from a scientific fascination into a very real obstacle. What's truly mind-bending is that some cosmic rays carry energies millions of times greater than anything we can produce in particle colliders. Scientists are still unraveling how nature accelerates particles to such extreme speeds, making cosmic rays one of the universe's most enduring mysteries. So while they might be invisible, their influence stretches from the depths of space to the very building blocks of life. And with that, we're ready to uncover another force lurking in the fabric of reality itself. But now, let's peel back another layer of the universe's mysteries, something so subtle, it's hidden in the very emptiness of space itself. We're talking about vacuum energy, the invisible hum of quantum fluctuations that fill what we once thought was nothingness. Even in a perfect vacuum where all matter and light have been removed, the universe is far from silent. At the tiniest scales, particles and antiparticles constantly blink in and out of existence, creating a seething sea of energy that defies our everyday intuition. This bizarre phenomenon isn't just theoretical, it might hold the key to one of cosmology's biggest puzzles. Some scientists believe vacuum energy could be the engine behind dark energy, the mysterious force accelerating the expansion of the universe. If true, it would mean that the empty space between galaxies is actually brimming with an invisible pressure, pushing everything apart faster and faster. Yet here's where things get thorny. When physicists try to calculate how much energy these quantum fluctuations should produce, the numbers are catastrophically wrong, off by a factor of 1 followed by 120 zeros. This staggering mismatch, known as the cosmological constant problem, remains one of the most embarrassing gaps in modern physics. It suggests we're missing something fundamental about how gravity and quantum mechanics intertwine. Could vacuum energy still be the answer, just in a way we don't yet understand? Or is dark energy something entirely different? For now, this cosmic tug-of-war between theory and observation keeps physicists awake at night, proving that sometimes the most powerful forces aren't the ones we can see, but the ones hiding in plain sight. And with that, we're ready to confront a force that turns matter into spaghetti. Now, let's turn our attention to a force that stretches the very fabric of reality: tidal forces. These aren't just the ocean tides you're familiar with. In space, tidal forces are the brutal result of gravity's uneven pull. Picture this: when an object gets too close to a black hole, the side nearest to it feels a far stronger tug than the side farther away. This difference in gravity stretches the object into a long, thin strand, a process so dramatic, scientists call it spaghettification. It's like cosmic pasta making, where stars, planets, or even unlucky spacecraft get pulled apart atom by atom. But tidal forces aren't just destructive. Take Jupiter's moon Io, the most volcanic place in our solar system. Jupiter's immense gravity doesn't just yank on Io evenly, it squeezes and stretches the moon as it orbits, generating intense friction inside. This friction heats Io's interior to the point where it erupts in massive volcanoes, spewing lava hundreds of miles into space. Without tidal forces, Io would be a cold, dead world. Instead, it's a fiery testament to gravity's hidden power to shape and energize. What's truly mind-bending is how these forces reveal gravity's hidden complexity. It's not just a simple pull, it's a gradient, a spectrum of intensity that can tear things apart or cook them alive. Whether it's black holes turning stars into spaghetti or Jupiter turning a moon into a pressure cooker, tidal forces remind us that gravity is anything but gentle. And as we'll soon see, the universe has even more ways to bend and warp the rules we think we know. Now, let's shift our gaze to another invisible powerhouse shaping the cosmos: magnetic fields. These unseen forces weave through the universe from the smallest planets to the grandest galaxies, orchestrating some of the most spectacular phenomena we know. Take Earth's magnetosphere, for example. This protective bubble, generated by our planet's churning molten core, acts like a cosmic shield. It deflects the sun's deadly solar winds, those streams of charged particles that could otherwise strip away our atmosphere. Without this magnetic embrace, life as we know it might never have taken hold. But Earth isn't the only celestial body with a magnetic personality. Look at the Sun, a swirling ball of plasma where magnetic fields twist and snap, unleashing solar flares and coronal mass ejections. These eruptions can disrupt satellites, knock out power grids, and even paint the skies with auroras, nature's own light show. And then there are neutron stars, the dense remnants of supernova, with magnetic fields so intense they could erase your credit card from 500,000 miles away. Zoom out further and you'll find magnetism stitching together the fabric of our galaxy. The Milky Way is threaded with a vast magnetic web, invisible lines of force that guide cosmic rays and shape the birth of stars. Scientists are still unraveling how these galactic fields form, but one thing's clear: magnetism is a universal sculptor, quietly shaping the universe from the smallest particles to the largest structures. So the next time you use a compass or marvel at the northern lights, remember, you're witnessing just a glimpse of the magnetic forces that bind the cosmos together. And as we'll soon see, the universe has even more hidden threads pulling at the tapestry of reality. Now, let's turn our attention to the most abundant state of matter in the universe: plasma. Often called the fourth state of matter, plasma is a superheated, electrically charged gas where atoms are stripped of their electrons, creating a sea of free particles. This fiery, dynamic substance isn't just common, it's everywhere. In fact, over 99% of the visible universe is made of plasma, from the blazing cores of stars to the vast, diffuse clouds drifting between galaxies. Take our Sun, for instance. Its searing surface and explosive corona are pure plasma, a roiling soup of charged particles that generate the solar winds we discussed earlier. These winds, streaming outward at nearly 1,000,000 miles per hour, carry plasma across the solar system, shaping planetary atmospheres and even influencing Earth's weather. And when the Sun's magnetic fields twist and snap, they hurl massive plumes of plasma into space, coronal mass ejections that can spark geomagnetic storms and dazzling auroras. But plasma's influence doesn't stop at our cosmic neighborhood. The interstellar medium, the sparse material filling the gaps between stars, is also brimming with plasma. This tenuous yet pervasive substance plays a key role in star formation, as gravity pulls these charged clouds together until they ignite into new suns. Even the glowing tendrils of nebulae, those celestial nurseries where stars are born, are sculpted by plasma's interplay with magnetic fields. Here on Earth, scientists are harnessing plasma's potential in groundbreaking ways, particularly in fusion energy research. By replicating the processes that power stars, fusion reactors aim to create clean, limitless energy by fusing plasma's atomic nuclei, a challenge that could revolutionize how we power our world. So whether it's lighting up the cosmos or fueling the dreams of clean energy, plasma is a force that truly defines the universe. And as we'll see next, even the coldest corners of space hold secrets just as astonishing. Now, shifting our gaze to a force that governs the very fabric of reality itself: entropy. This isn't just a scientific concept, it's the universe's silent rulebook, dictating why things fall apart, why time only moves forward, and why even the cosmos can't escape its grip. At its core, entropy is a measure of disorder, and the second law of thermodynamics states that in any isolated system, it always increases. Think of it like a sandcastle on the beach. No matter how carefully you build it, wind and waves will eventually scatter the grain. The universe works the same way, forever marching toward chaos. This relentless rise in entropy gives time its arrow, the reason we remember the past but not the future. Drop an ice cube into warm water and it melts, never the other way around. Shatter a glass and the pieces don't spontaneously reassemble. These everyday examples hint at a cosmic truth. Disorder is the default, and every process from the fusion in stars to the thoughts in your brain contributes to it. But entropy's reach extends far beyond broken cups and melting ice. It points to the universe's ultimate fate, the so-called heat death. Imagine a future where all stars have burned out, black holes have evaporated, and the cosmos is left as a vast, lukewarm sea of particles, too dispersed to fuel any new activity. This isn't science fiction. It's the inescapable end predicted by thermodynamics, where maximum entropy leaves the universe in a state of perfect, lifeless equilibrium. Yet entropy isn't just about doom and decay. It's also the reason life exists at all. The flow of energy from hot to cold, from order to disorder, powers everything from thunderstorms to photosynthesis. Without entropy, there'd be no weather, no seasons, no complexity, just a static, unchanging void. So while it spells the universe's eventual end, it's also the force that makes the present so vibrant and dynamic. And as we'll soon see, even in the face of this cosmic unraveling, the universe holds mysteries that defy simple explanations. Now, let's step into the bizarre and mind-bending world of quantum entanglement, where particles defy the rules of classical physics in ways that even Einstein called spooky action at a distance. Imagine two particles born from the same quantum event, separated by vast distances, yet somehow, changing the state of one instantly affects the other, no matter how far apart they are. It's as if they're dancing in perfect sync across the cosmos, connected by an invisible thread that ignores space and time. This phenomenon isn't just theoretical. Experiments have repeatedly confirmed that entangled particles share a mysterious link, with measurements on one instantly determining the state of its partner. Einstein himself struggled with this idea, arguing it violated relativity's speed limit. Nothing, not even information, should travel faster than light. Yet quantum mechanics insists this connection happens without any physical signal, leaving scientists to grapple with its paradoxes. But entanglement isn't just a puzzle, it's a gateway to revolutionary technologies. Quantum computers harness entangled particles to perform calculations at speeds unimaginable to classical machines, solving problems like drug discovery or climate modeling in seconds. Quantum communication using entangled photons could create unhackable networks where any eavesdropping would instantly break the delicate link, alerting users to interference. And here's the real kicker: entanglement might even rewrite our understanding of reality itself. Some theories suggest the universe's very fabric could be a vast web of entangled particles, with every event subtly influencing every other. It's a humbling reminder that the cosmos still holds secrets far stranger than fiction. So while entropy pulls the universe toward disorder, entanglement weaves a hidden order beneath the chaos, one we're just beginning to unravel. And as we'll see next, even deeper mysteries await in the quantum realm. Now, let's turn our attention to something even more fundamental: the Higgs field, the invisible cosmic stage that gives particles their mass. Picture the universe as a grand theater and every particle as an actor moving through it. Some glide effortlessly like photons which have no mass. Others, like electrons and quarks, seem to slog through as if wading through molasses. That resistance, that's the Higgs field at work. This field isn't just some abstract idea. In 2012, scientists at the Large Hadron Collider confirmed the existence of its signature particle, the Higgs boson, a discovery that completed the standard model of particle physics. Think of the Higgs boson as a ripple in the field, proof that the field itself is real. Without it, particles would zip around at the speed of light, never clumping together to form atoms, stars, or us. Here's how it works. As particles move through the Higgs field, they interact with it. The more they interact, the more mass they gain. Protons and neutrons, for example, are heavy because their constituent quarks engage strongly with the field. Neutrinos, on the other hand, barely interact, which is why they're nearly massless. This delicate interplay shapes everything from the tiniest atoms to the largest galaxies. But the Higgs field isn't just about mass, it's about diversity. Without it, the universe would be a bland soup of identical, weightless particles. Instead, thanks to this invisible scaffold, matter can take on countless forms, enabling the complexity that leads to planets, life, and even the device you're using right now. And while we've uncovered its role, mysteries remain. Why does the Higgs field have the strength it does? Could it change over time, altering the very fabric of reality? These questions remind us that even the forces we think we understand still hold secrets waiting to be revealed. Up next, we'll venture into the realm of theoretical shortcuts across spacetime wormholes, where the rules of physics bend in ways that might just make interstellar travel a possibility. Now, let's take a leap into one of the most mind-bending concepts in physics: wormholes, the cosmic tunnels that could theoretically connect distant parts of the universe in an instant. Imagine folding a piece of paper so 2 points touch, then poking a hole through them. That's the basic idea behind a wormhole, a shortcut through the fabric of spacetime itself. The concept isn't just science fiction. It stems from Einstein's theory of general relativity, where he and physicist Nathan Rosen proposed something called Einstein-Rosen bridges. These bridges are solutions to the equations of relativity that could link two black holes, creating a passage between them. But here's the catch: these natural wormholes would be incredibly unstable, collapsing faster than anything could pass through. To keep a wormhole open long enough for travel, you'd need something truly exotic: negative energy or matter with repulsive gravity. This bizarre substance could counteract the wormhole's tendency to snap shut, acting like a cosmic support beam. The problem: we've never observed negative energy in nature, and creating it in a lab would require technology far beyond our current reach. Yet, the idea tantalizes scientists because wormholes wouldn't just bridge space, they could bridge time too. Traversing one might allow you to emerge in a different era, making them potential time machines. Of course, the paradoxes this creates, like going back to meet your past self, raise questions about whether the universe would even allow such a thing. While wormholes remain speculative, they push the boundaries of our understanding, challenging us to rethink the rules of physics. Up next, we'll explore another cosmic enigma: white holes, the hypothetical opposites of black holes that might just rewrite our cosmic playbook. Now, shifting our gaze to another cosmic mystery, let's unravel the enigma of white holes, the theoretical opposites of black holes. If a black hole is a cosmic vacuum cleaner, sucking everything in and never letting go, a white hole would be its polar opposite, a cosmic fire hose, spewing out matter and energy with no way to enter. Picture a black hole running in reverse. Instead of pulling everything in, it violently expels everything out, defying the laws of physics as we know them. The idea of white holes emerges from the same equations of general relativity that predict black holes. In fact, some theories suggest that a white hole could be the other end of a black hole's tunnel, like a hidden exit in the universe's labyrinth. But here's where it gets even wilder. Some scientists speculate that the Big Bang itself might have been a white hole event, a sudden eruption of space-time and matter that birthed our universe. Yet, despite their fascinating potential, white holes remain purely hypothetical. Unlike black holes, which we've observed through their gravitational effects and even photographed, white holes leave no trace in our cosmos. One reason could be their inherent instability. While black holes form naturally from collapsing stars, white holes would require conditions so extreme that they might only exist for a fleeting moment before collapsing into something else or simply fizzling out. Another possibility is that white holes are forbidden by the universe's own rules. The second law of thermodynamics, which dictates that disorder always increases, might prevent white holes from existing because they'd essentially be reversing entropy, a cosmic no-no. Or perhaps they're hiding in plain sight, masquerading as other phenomena we haven't yet decoded. Whether white holes are real or just a quirk of math, they challenge us to think differently about the universe's boundaries. Up next, we'll dive into the ghostly world of neutrinos, particles so elusive they pass through entire planets like they're not even there. Now, let's turn our attention to one of the universe's most elusive inhabitants, neutrinos. These ghostly particles are so light they almost don't exist, yet they play a starring role in some of the cosmos' most dramatic events. Imagine a particle so tiny it can zip through an entire planet like it's empty space. That's a neutrino for you. Billions pass through your body every second, leaving no trace behind. What makes neutrinos so fascinating is their near masslessness. They're so lightweight that for decades scientists thought they had no mass at all. But groundbreaking experiments revealed they do have a tiny bit of heft, just a fraction of what an electron weighs. This discovery reshaped our understanding of particle physics and even hinted at mysteries beyond the standard model. Neutrinos are also cosmic messengers, especially from supernova. When a massive star explodes, it floods the universe with these particles, carrying secrets about the explosion's inner workings. In fact, when supernova 1987 lit up the sky, detectors on Earth caught a handful of neutrinos hours before the light arrived, proof of their role as early warning signals from dying stars. Catching these shadowy particles is no easy feat. Detectors like Ice Cube, buried deep in Antarctic ice, wait patiently for the rare moment a neutrino collides with an atom, creating a faint flash of light. These detectors are like cosmic fishing nets, snaring neutrinos that have traveled billions of light years to reach us. Whether they're revealing the hearts of exploding stars or challenging our grasp of physics, neutrinos remind us that even the smallest things can have universe-sized implications. Next up, we'll witness the ripples in spacetime itself, gravitational waves, and how they've opened a new window into the cosmos. Now, let's dive into something that sounds like science fiction but is very real: gravitational waves. These ripples in the fabric of spacetime were first predicted by Einstein over 100 years ago, but it wasn't until 2015 that humanity finally caught them in action. Thanks to the Laser Interferometer Gravitational Wave Observatory, or LIGO, we witnessed spacetime itself stretching and squeezing as two black holes collided over 1 billion light-years away. What's incredible about gravitational waves is how they reveal cosmic events we'd otherwise never see. Black holes, for example, don't emit light; they're invisible. But when two of them spiral into each other, they send out these waves like ripples from a stone dropped in a pond. LIGO detectors, with their ultra-sensitive lasers, pick up these tiny distortions, changes smaller than the width of an atom. This discovery didn't just confirm Einstein's theory, it opened a whole new way to explore the universe. Before gravitational waves, astronomy relied on light, visible X-ray radio. Now we have another sense, like hearing the cosmos for the first time. And when combined with traditional telescopes, it's called multi-messenger astronomy, giving us a fuller picture of events like neutron star collisions, which produce both gravitational waves and flashes of light. The most mind-blowing part: these waves travel at the speed of light, carrying information about some of the most violent events in the universe: black hole mergers, supernova, even echoes from the Big Bang itself. Every detection peels back another layer of cosmic mystery, showing us just how dynamic and interconnected the universe really is. With gravitational waves, we're not just observing the cosmos, we're feeling its heartbeat. And as detectors grow more sensitive, who knows what else we'll discover? Next, we'll turn our gaze to the universe's most precise timekeepers, pulsars, and how their rhythmic flashes help us map the stars. Now, shifting our focus from the ripples of spacetime to the steady beats of the cosmos, let's talk about pulsars, nature's most precise cosmic clocks. These incredibly dense neutron stars spin at mind-bending speeds, some rotating hundreds of times per second, sending out beams of radiation like interstellar lighthouses. Every time one of these beams sweeps past Earth, we detect a pulse of light or radio waves, hence the name pulsar. What makes pulsars truly remarkable is their near-perfect regularity. Their pulses are so consistent that they rival the best atomic clocks we've built here on Earth. This precision has made them invaluable tools for testing Einstein's theory of general relativity. For example, when astronomers discovered a pulsar orbiting another neutron star, they watched as the pulses slowed down and sped up in perfect agreement with Einstein's predictions about how massive objects warp spacetime. It was like having a cosmic laboratory to prove relativity in action. But pulsars aren't just cosmic timekeepers, they've also played a starring role in the hunt for planets beyond our solar system. In the early 1990s, astronomers detected tiny irregularities in the pulses from a pulsar named PSRB 1257+12. These slight timing variations hinted at the gravitational tug of orbiting planets, the very first exoplanets ever discovered. While these worlds are nothing like Earth, bathed in intense radiation and likely barren, their discovery opened the door to the thousands of exoplanets we've found since. Pulsars continue to surprise us. Some, called magnetars, have magnetic fields so strong they could strip the data off a credit card from halfway across the solar system. Others, like the famous Crab pulsar, are the remnants of supernova observed nearly 1,000 years ago. And with new telescopes scanning the skies, we're finding even more of these cosmic beacons, each one offering fresh insights into the extremes of gravity, matter, and time. So, while gravitational waves let us feel the universe's heartbeat, pulsars give us its rhythm, a steady, reliable cadence that guides our understanding of the cosmos. Up next, we'll rewind all the way to the beginning, to the force that started it all, the Big Bang. Now, let's journey back to the very beginning, the moment that set everything in motion. The Big Bang wasn't just an explosion in space, it was the birth of space and time itself. Imagine the entire universe compressed into an unimaginably hot, dense point, smaller than a single atom. Then, in a fraction of a second, it expanded faster than light itself, laying the foundation for everything we see today. The evidence for this cosmic dawn is all around us. Take redshift, for example. When astronomers look at distant galaxies, they notice their light is stretched toward the red end of the spectrum, like the sound of a passing ambulance siren dropping in pitch. This tells us those galaxies are moving away from us, proof the universe is still expanding from that initial burst. Then there's the cosmic microwave background, or CMB, a faint glow of radiation filling the sky. It's the afterglow of the Big Bang, cooled over billions of years to just a few degrees above absolute zero. This ancient light is like a baby picture of the universe, capturing its structure when it was only 380,000 years old. Yet for all we've uncovered, the Big Bang leaves us with tantalizing mysteries. What triggered it? Was there something before it, or did time itself begin there? Some theories suggest a multiverse, where our universe is just one bubble in a vast cosmic foam. Others propose cyclical models where universes collapse and rebirth endlessly. And then there's the question of what caused that rapid inflation in the first moments. Was it a quantum fluctuation, or something even stranger? The Big Bang isn't just a theory about the past, it's a window into the deepest questions of existence. As we piece together clues from the CMB, galaxy distributions, and even gravitational waves, we're not just studying how the universe began, we're uncovering the story of how everything, including us, came to be. Next, we'll push the boundaries even further, exploring the mind-bending idea that our universe might not be the only one out there. Now, let's stretch our imaginations beyond the familiar cosmos and into the realm of the multiverse. Picture our universe not as a solitary island, but as one of countless others in an endless cosmic ocean. This is the multiverse theory, a mind-bending idea that challenges everything we thought we knew about reality. One version of this theory, called the inflationary multiverse, suggests that our universe is just one bubble in a vast, ever-expanding foam of universes. During the Big Bang, space may have inflated at different rates in different regions, creating isolated pockets, each with its own unique laws of physics. Some might have stars and planets like ours, while others could be utterly alien, with different constants of nature or even extra dimensions. Then there's string theory, which proposes a landscape of possible universes, each a different solution to the equations governing reality. Think of it like a cosmic tuning dial. Tweak one parameter, and you get a universe where gravity is stronger or atoms can't form. In this view, our universe's fine-tuned conditions might just be a lucky roll of the dice in a sea of possibilities. Quantum mechanics adds another layer with the idea of branching universes. Every time a particle faces a choice like whether to spin left or right, the universe might split into two, creating parallel timelines. It's like a never-ending tree of possibilities where every decision spawns a new reality. But how do we test these ideas? Some scientists look for clues in the cosmic microwave background, searching for imprints of collisions with other universes. Others hunt for anomalies in particle physics that might hint at hidden dimensions. The challenge is that most multiverse theories lie beyond our current observational reach, sparking debates about whether they're science or philosophy. Yet the implications are staggering. If the multiverse is real, it reshapes our place in the cosmos. Are we just one outcome in an infinite tapestry of realities? Does it make our existence more or less meaningful? These questions blur the line between physics and metaphysics, reminding us that the universe, or multiverse, still holds mysteries we've only begun to explore. Next, we'll venture into an even more speculative frontier, the idea that consciousness itself might shape reality. Now, let's take a step into one of the most profound mysteries of all, the idea that consciousness itself might be a fundamental force in the universe. What if the act of observation doesn't just record reality but actually shapes it? This isn't science fiction, it's a serious debate at the edge of physics and philosophy. One radical theory, called panpsychism, suggests that consciousness isn't something that emerges from complex brains, but is instead woven into the fabric of reality itself. In this view, even the smallest particles might have some rudimentary form of awareness. Imagine if electrons or atoms had a tiny spark of experience, not thoughts or feelings as we know them, but a basic capacity to feel their existence. It's a wild idea, but some thinkers argue it could solve the puzzle of how subjective experience arises from lifeless matter. Then there's the quantum mind hypothesis, which ties consciousness to the strange behavior of particles at the smallest scales. In quantum mechanics, particles exist in a haze of possibilities until they're observed. Then they choose a definite state. Some scientists, like Nobel laureate Roger Penrose, speculate that this collapse might be linked to processes in our brains. Could our minds be quantum computers, tapping into the fundamental uncertainty of the universe to generate thoughts and free will? But the biggest question is this: does the universe need an observer to exist? In quantum experiments, particles seem to know when they're being watched, behaving differently under measurement. This has led to interpretations like the participatory universe, where reality is a kind of dialogue between the observer and the observed. It's as if the cosmos is a vast, self-aware network, with consciousness not just a product of the universe but a key player in its very structure. Of course, these ideas are fiercely debated. Critics argue they blur the line between science and metaphysics, lacking testable predictions. Yet, if even a sliver of this is true, it would redefine our place in the cosmos. Are we passive witnesses to the universe or active participants in its unfolding story? The answer might lie at the intersection of physics, neuroscience, and something even deeper: the nature of existence itself. As we wrap up our journey through the universe's most powerful forces, remember this: whether it's gravity bending space-time or consciousness shaping reality, the cosmos is far stranger and more wondrous than we ever imagined. Stay curious, keep questioning, and who knows, maybe one day you'll help unlock the next great cosmic mystery. If you enjoyed this exploration, don't forget to subscribe for more mind-expanding content. Hit the bell so you never miss an update, and let us know in the comments which of these forces fascinates you the most. Thanks for watching, and see you in the next adventure. From the invisible grip of gravity to the mind-bending possibilities of consciousness, we've journeyed through the 30 most powerful forces shaping our universe. Each one, whether it's the explosive fury of supernova or the eerie influence of dark matter, reveals just how dynamic and mysterious the cosmos truly is. Together, these forces weave the grand tapestry of reality, from the smallest quantum flickers to the vast dance of galaxies. Humanity's quest to understand these phenomena is more than just scientific curiosity, it's a story of awe and perseverance. Every discovery, from Newton's apple to the detection of gravitational waves, brings us closer to unraveling the universe's secrets. Yet with each answer comes new questions, reminding us that the cosmos always has another layer of wonder to reveal. So keep looking up, stay curious, and never stop asking, what if? The universe is full of mysteries waiting for minds like yours to explore them. If you loved this cosmic adventure, make sure to subscribe and hit the bell so you don't miss our next dive into the unknown. Drop a comment below which force left you the most amazed. Thanks for joining us on this journey through the universe's greatest powers, and until next time, keep wondering.